Hello everyone. I hope you guys are still doing well. And previously you guys were introduced to work in lesson, what lesson was that? I think it was lesson 15. So I would suggest that if you're not really familiar with the concepts of work and energy, you should first watch that lesson. But for today's lesson, it's really going to be more theoretical than doing calculations, and then the next lesson we're going actually to be doing calculations on work and energy, especially treating previous question papers. So we've already been introduced to work, like I've mentioned, and this is a document, this is an examination guideline document that I think you guys have, if I'm not mistaken, and then you should be able to define the work done on an object by a constant force F. So work is done by a constant force as the product of the force multiplied by the displacement, which is the change in x, multiplied by the cos of theta. And now they tell us that F is the magnitude of the force. So let's highlight that. And then the change in x is the magnitude of the displacement. So now if your object was moving vertically, this would actually be a change in y, given that the work done is also in the direction of the displacement, or is parallel to that displacement, meaning that it was vertical as well. And the angle theta, which is a very important thing, that angle is the angle between the force in question and the displacement. So I say the force in question because sometimes you might be asked to calculate the work done by friction. So you should be able to find the angle between the force of friction as well as the displacement. And then now they're just giving us what you should not say in exam. You should not and never mention that work is done against the force. There is no such thing. Work, a force does work. It's not a thing of work is done against the force. Okay, so now let us move on. Another thing that is important, and we've already done this in lesson 13, where you have to draw a free body force diagrams as well as free body diagrams. That is very important. You still need that knowledge, especially when we're performing calculations with work. You'll see in the next lesson, and also be able to calculate the net work done. In the last lesson we touched a little bit on this, as well as that you should be able to differentiate between positive net work as well as negative net work done on the system. So you should be able to tell us when work is done, what does it mean when it's negative and what does it mean when it's positive. I've already touched on that in the previous lesson. So if you don't know, please refer back to lesson 15. And then another important thing that is common, or I'm not sure why I'm saying common, another important thing is that you should be able to state the work energy theorem. So the nice thing about this examination guidelines is that they actually give you the accepted definitions. So you should really familiarize yourself with this examination guidelines, so you know exactly what is it that you must say and what is it that you must not say in exams, right? And the work energy theorem says that the work done on an object by a net force is equal to the change in the object's kinetic energy, or the work done on an object by a net force is equal to the change in the object's kinetic energy. That feels like a repetition, but essentially in symbols what that is saying is that W net, which is the work done by a net force, is equals to the change in kinetic energy. And if you talk about a change in kinetic energy, we mean it's the final kinetic energy minus the initial kinetic energy. So additionally, you should be able to apply the work energy theorem on objects on horizontal. So if you've given an object on a horizontal surface, you should be able to apply the work energy theorem vertical as well as inclined planes. Inclined planes, remember those ones that are on a slope, for both frictionless and rough surfaces. So remember, rough surfaces have friction. Okay, let us just move a bit down. Another thing that is important in terms of work and energy is the conservation of energy with non-consecutive forces present. So you should be able to differentiate between two terms. What do we mean by a conservative force, as well as what is it that we mean by a non-conservative force. So a conservative force is defined as a force for which the work done in moving an object between 2 points is let me remove this. How do you delete this? Delete this. Okay. Though it's a force for which the work done in moving an object between 2 points is independent of the path taken. Examples are gravitational force. So for example, whether your object is moving to the left or to the right, or it's moving up or down, gravity will always be pulling your object down. Another example is the elastic force in a spring and the electrostatic forces or Coulombic forces. So know that definition. And then another thing is that non-conservative forces are defined as forces for which the work done in moving an object between 2 points depends on the path taken. So examples, we're talking about frictional forces, air resistance, as well as tension. So note the difference. Conservative forces are independent of the work of the path taken. Like I mentioned, gravity is always down, no matter whether your thing is moving to the left, to the right, or up or down. And then non-conservative forces, they are dependent on the path taken. Frictional force, if your object is moving to the left, frictional force will be pulling or resisting motion, meaning it will be kind of pushing to the right, and then, or pulling to the right. And then if your object is moving to the right, frictional forces will now be pulling to the left. So it actually is dependent on the path taken. Its direction changes depending on the path taken. For this one, the direction of the gravity does not change whether or not you're moving to the right or to the left. Another thing, we've already touched on this when we talked about conservation of mechanical energy. So this was in lesson 6. So you should be able to state the principle of mechanical energy. So now I want you to realize that how all of these topics are all kind of tying together when we talk about work. So everything that you've learned about forces, everything that you've learned so far about energy is all now just tying together when we talk about work. And we said that the total mechanical energy, which is the sum of the gravitational potential energy and kinetic energy in an isolated system, that's a key word there, in an isolated system, remains constant or is conserved. You should know that, you should know it, you should memorize that in your brain somewhere. And then now they give us a what they mean, and we've already talked about this. What is an isolated system? And is when there is no net external forces. So when we talk about external forces in lesson, we've already spoken about this. We can maybe talking about friction and all of these other external forces. And then you should be able to solve problems that include the principle of conservation of energy using this equation. So this is another equation. So be mindful that we've already introduced you to 3 equations that we're going to use in the next few lessons, or in the next lesson when we do previous question papers. And now you should also be able to use the relationship above to show that in the absence of non-conservative forces, so if your system is isolated, I'm lying, in an isolated system, that's when we don't have non-conservative forces such as friction. Mechanical energy is conserved. So yeah, this brings us to the end of this lesson. I hope you guys actually go through this lesson, go through it, as well as looking at those examination guidelines, so that they can actually guide you as what is important in an exam. Accepted definitions, memorize them and know them. Thank you so much for watching.